Okay, so number 52 is an example of a linear thought process. And the reason I really want to talk about this is, one, talking about the utility belt, which we bring to every exam, and we want to bring everything we can to the exam. And then two, talking about Bernoulli's principle and how to think about a traffic analogy. In short, the higher the speed, the lower the pressure, and the lower the speed, the higher the pressure. Okay, but let's get back to number 52, and then I'll explain how all this makes sense. So for this question, 16-year-old boy with VATER syndrome was brought to the physician because of a 2-week history of harsh cough that began with a common cold. All right, pause. First of all, I gave the answer here because it's D, because the answer is not really what we're after. We're trying to understand the entirety of the question, and not only why the answer is the answer, but why are the wrong answers even here, and then how do all these sentences and lines lead us to the answer of D and lead us away from all these other answers. I won't get into the nitty-gritty of everything that we're talking about, and like how like why this blood pressure is this blood pressure and why is the temperature such as it is. But what I want to say is, basically, if you look at VATER syndrome, I didn't really know what they were talking about to begin with, because I didn't know anything about VATER syndrome, but I knew about VACTERL syndrome. And I realized, okay, either this is a different acronym, like from a previous, era of like talking about VACTERL syndrome, or this is simply that, in the best case scenario, this person has less symptoms than we would expect. It doesn't turn out to be the case, I think. But VACTERL syndrome is, vertebral anomalies, anal atresia, cardiac anomalies, tracheoesophageal fistula, renal and limb malformation. So if you didn't know anything about anything, right? If the only thing that you brought in your utility belt was the English language, and you read VATER syndrome, right? And you had, it's not a guess necessarily, but not even an educated guess, but you can make an educated inference about what's going on based on these answer choices, because this acronym has to begin with these letters, right? And there's only one of these letters that lines up here. Okay, so just off rip, you could probably get the right answer just by being able to read the question properly. And that's why I wanted to talk about this to begin with. The second thing I wanted to talk about was Bernoulli's principle, and specifically the forced vital capacity, or the fast vital capacity, is 78%, and the slow vital capacity is 85%. So here they're giving us the element of time, and they're asking us, okay, make sense of what's going on here. They also give us this flow volume loop, and then they ask us, okay, literally, how do you explain this discrepancy between the patient's forced vital capacity and slow vital capacity? So what you can think about really is Bernoulli's principle. That's really what they're trying to get after. And the best way that I thought about it to begin with was talking about like a garden hose. If you have a certain amount of water that's coming out of the hose and then you put your thumb on it, right? I know it's a poor rendition of a thumb, but it's a thumb, okay? What's actually going to happen is you're going to be increasing the backup pressure here. And so what's going to happen is there's actually going to be the same amount of water is flowing out, the same amount of water has to flow out through the end of this pipe, but now it's going to be going at a much higher speed. And why is that? Because the pressure is actually lower. So you're creating like a pressure vacuum in this area right here. That may be a little bit complicated, which is why I wanted to talk about the traffic analogy, because it makes way more sense. Okay, so if you're going to work, if you're going to the hospital, if you're going to school, anything that you're trying to do, right? If there's no traffic and you're moving at a high speed, you're like, all right, I'm not pressed. There's no pressure in this situation. I'm going to get there when I need to get there, right? Forget about this for a second. But now if there's like 8 a.m. traffic and there's standstill traffic and everyone's trying to get to where they're going, and on top of that, they have a lane closed for construction, what's going to happen is everyone is moving at a very slow speed, and everyone is feeling a lot more pressure because they're trying to get places and they're not moving anywhere. They're trying to progress and they're not being able to progress. Okay, and then these people in this lane are going to switch over because this lane is not moving. So they're going to have to they're going to force more and more people into these 3 lanes, right? And then what's going to happen is, okay, right after you get to that point, right here, after you get to this point where the lane is now open, this person over here and all these people, once they get past the point where they can move freely, they're going to try to move into this lane because it's empty and they're trying to get places. And now what I mean to say is there's less pressure in this area. Right after you get to the construction point, there's less pressure. And so because of that, there's more speed. That's what I mean. Like it's always inversely related. As the speed increases, the pressure decreases. So it's the best way to think about it is really using the traffic analogy. Getting back to the question about the actual, why is it tracheal collapse, right? If you think about these cars as like air molecules, if you're literally blowing out the air, what happens is the air that was here is now expelled out, and that creates a relative pressure vacuum here. So the vacuum is going to collapse, right? That's what happens in the trachea. It collapses, and The reason they give you VATER syndrome or VACTERL syndrome is because this person's trachea, if you think about it in this way, the anterior and the posterior, and I'll talk. So the reason you think about it this way is because cars in the right lane move a little bit slower than they do in the left lane. Generally, the left lane is always going to be moving faster. And there's this rigidity, there's this slowness in the right lane. That's what happens in the trachea, unless, right, you have these bones, or you have the trachea set up in such a way where the cartilage and everything in the trachea makes it a little bit more rigid, unless you have VATER syndrome. And so that's what they're trying to talk about in this question. And then finally, the last thing I want to say is, okay, right after you have this decrease in pressure, right after this little construction has ended, what you can also do then is, if there's another avenue for cars to get in, cars will be like, okay, this lane is totally open, I'm just going to get in this lane right here, right? And that's what ends up happening when we use a Venturi mask, right? So the Venturi mask, what actually happens is we give patients a certain amount of oxygen, and then we design the Venturi mask in such a way where it allows oxygen, like room air, to come in as well to help the patient. So that's basically the idea behind number 52. And again, that's a linear thought process, because what they're trying to do is they don't give you all the points, right? They try to give you a few things like VATER syndrome or VACTERL syndrome, and then they want you to think downstream, like what's happening because this person's trachea is a little floppy, right? Because this person doesn't have the rigidity that they have, right? What's going to happen with the air molecules? Are they going to be a little bit more floppy? Are they going to be able to flow out? And if that flow out as fast, right, what's going to happen to the actual trachea? Is it going to collapse? And that's what happens, right? So again, I hope this this video was useful and helpful, and please let me know if I can do more.